very good evening to all our esteemed participants. Welcome to session 11 of AICT Training and Learning Academy sponsored faculty development program on quantum machine learning, bridging the gap between quantum computing and AI. We hope you have been enjoying this journey of exploration into the exciting intersection of quantum computing and artificial intelligence. This session promises to be particularly fascinating as we delve into the engineering challenges currently faced by developers of quantum computers. Quantum computing is a field filled with immense promise, but its development comes with unique and complex challenges. Understanding these hurdles is key to advancing this transformative technology. Our distinguished speaker for this session is Dr. Neeraj Kumar. Dr. Neeraj Kumar is an assistant professor in the Department of Information Technology at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. He holds a PhD in Information Technology with a specialization in IoT and AI from BBAU Central University, Lucknow, and an MTech in IT with a focus on wireless communication and computing from IIIT Allahabad, supported by an MHRD teaching assistantship. He also earned his BTech in CSE from UPTU Lucknow. Dr. Neeraj has been a faculty in the Department of CSE at UPTU from 2006 to 2013. An accomplished researcher, he has published numerous papers in reputed international journals and conferences, including those by IEEE and Springer, and authored over a dozen patents and books on advanced topics. His research interests encompass machine learning, computer vision, IoT, security, big data analytics, and soft computing, contributing significantly to these domains. Before we begin, we kindly request all the participants to keep their microphones muted to ensure a smooth session. If you have any question, please type them in the chat box. Without further ado, let us warmly welcome Dr. Neeraj Kumar. Over to Dr. Neeraj, sir.
Okay. Thank you very much, Dr. Goyal.
Thank you, sir.
First, I'm very thankful to all your management that has been actually invited me for this very good talk. Now, I think you have already seen the PPT, and I'm just going to share this PPT. So, today in this session, I think it is visible to all of the participants. If it is not visible to any one participant, just inform me through
Sir,
the
please
chat
share
box.
in presentation mode.
It is perfectly visible, and my voice is audible, sir.
Yes, sir. Yes, sir.
Okay, so engineering challenges currently faced by developers. Now I'm just going to explain here. But before going to certain challenges, I am just want to say something about the quantum computing. Actually, I have written a book in 2018 on the quantum cryptography, and at that time I have just studied a lot of on the quantum mechanics, quantum computing, and the quantum cryptography. At that time I have seen a lot of challenges, and since 2008 to 2024 I am just watching the scene on the different forums, and the challenges are actually it is very interesting that challenges are actually as it is. So those are not actually uh, handled by the people or the researchers. So it is already now actually coming from the 2000, at least 2018 to 2024. So now I'm just want to say that little bit, I think it is a 11th session, so participant already now known about the quantum computing or the principle about quantum computing. I'm not just, that's why I'm not actually going in deep for that particular principles, but a little bit I'm just want to say, because these challenges you can understand better when just see these principles in my way. Okay, so let me start here. This is my uh, table of content that I'm going to discuss. Sir, slide is changing properly. Dr. Goyal?
Yes, sir. Yes.
Okay, so this is a content in which I have just divided the PPT into the five topics. First one is a introduction, second one is a principle, third one is a implementation. Principle and implementation both just showing the application of the quantum uh, computing or the quantum cryptography, and after that, on the basis of these applications, I'm just considering the challenges. Okay, that's why is a color coding a little bit actually explaining it also. Now it's the introduction. So in the introduction part, you will see the basic principles, how actually works. So basically three basic principle, however, three other additional principle also added just due to these basic principles. Okay, so first one is a qubit, second one is a superposition, and third one is a entanglement. Qubit is a number of bits that is utilized by a quantum computer or the QC for just equivalent to the 0 or 1 utilized by the classical computers or the traditional computers, you can say, or by the supercomputer also. All supercomputer, traditional computer, and are considered in the classical computer. So if I am saying some classical computer, then you can assume that it is also saying about the supercomputer or about the traditional computer or the calculator also. Okay, so 0 and 1 just utilized by the classical computer, while the qubits are utilized by our quantum computer or the QC. So principle of quantum mechanics basically depends on the three basic principle. First one is a qubit, second one is a superposition, and third one is a entanglement. Superposition basically utilized to just uh, to just make your algorithm faster, basically, while the entanglement makes every situation unique. On the other hand, qubit provides us a lot of options. Okay, so these three principle actually giving us three different paradigm. Qubit for a lot of options, superpositions for parallelism, you can say, or for the fast speed, or the entanglement just to provide us actually non, you can say, non duplicacy. Okay, so you can say the solution or the state will be unique due to the entanglement, and due to these three principles, another three principle just created, and those are also added into this, and that's why we say that there are only six basic principle for the quantum computing. It is just a figure of quantum computer. Most of the people generally is seen this in the each and every book, I think so. So now we are going to this classical versus the quantum bits. Once classical bits just used to utilize the 0 and 1. On the other hand, 0 and 1, when greater than or the mod in form of anything, then it's just considered as superposition. This principle just provides
Sir.
us parallel processing, so that's why it is just generates the parallelism. So again, I'm just saying that 0 and 1 utilized by classical computers, while 0 and 1 in form of mod utilized by a quantum computer. That's why these bits we just consider as a quantum bits, and it provides the parallel processing. So the parallelism is just utilized to provide the multiple states, or to process the multiple uh, algorithms simultaneously. When we can add up a new one. That's why it is just providing the scalability. You can just uh, process a lot of algorithms. We are no limit actually here, because if you are just increasing the number of qubit, you can utilize the more parallelism. Ultimately, just can scale up your uh, processing due to the superposition principle. Okay, now we are going on the principles. So principle of superposition just provides us few things. First one is a concept, just going to say 0 and 1 just as a classical computer, but here 0 and 1 just consider as a in form of mod, or in form of greater than, or in form of less than, but generally utilized by the greater than. So c naught oblique 0, c1 oblique 1, here c naught and c1 also impressed as a expressed as a alpha or the beta. So alpha and beta you can see in various literature, and in various literature you can see these as a c naught or the c1. Here alpha square plus beta square in case of mod just will be equal to 1. Okay, so this will be the meaning of that this expression actually. Next, it is just you can say when we are just spinning our coin, then it just provides head or the tail. But at the position of spinning, it is not providing the um, head exactly, or not providing the tail exactly. But when it is nearby head, then you can say it is on head position. It is nearby tail, you can say it is a tail position. In the same way, our expression provides us a lot of positions. That is the principle of superposition that makes it faster for the communication. So you can say that's why I have clarified it also. C naught and C1 are complex numbers that define the probability amplitude of each state. Okay, it is based on the probability basically. Next, you can say here I have just mentioned one qubit that is measured as a 0, and you can assume it as a far apart from the 0. That principle just considered as a spooky action at a distance. So spooky action is the principle basically. It is comes into the entanglement. You can say in the figure that if you are using 0 or the 1, if 0 is coming onto the x direction, and 1 coming in onto the y direction, then both directions having the same kind of relationship, that you can say correlation of two different systems. So it is just making a correlation. Entanglement just utilized to make a correlation that provides us a solution, or the unique solution at each stage. So you can say two or more qubits can be entangled, creating a correlation where the state of one qubit instantly determines the state of another regardless of the distance. So ultimately, before the two bits, there are no matter how much distance, but the situation actually matter here. So entanglement just provides the conditions by which both are attached actually. How both are correlated, this is just given by entanglement. Okay, next. It is a quantum parallelism just coming from the I have just already explained that parallelism just coming from the principle of superposition. Quantum computers can evaluate multiple possibilities simultaneously. That's why parallelism just comes into the existence. A most famous algorithm, that is the Shor's algorithm, provides the factoring a large number. A quantum computer can examine many possible factors in parallel due to the quantum parallelism. Okay, so it is just reducing the time. That's why you can see uh, a algorithm that is runnable in executable in 10,000 minutes just uh, may process within the few seconds using the quantum computers. It is due to the principle of superpositions that provides us the principle of parallelism basically. Next, it is a quantum interference. Quantum interference reach us on the solution. So this solution may be a negative or this solution may be a positive. So to provide us the decision making or the perfect decision making, interference actually provides us a path. You can say quantum systems can exhibit wave interference where probabilities combine constructively or the destructively to amplify the correct answer or the wrong answer. If both are wrong, then it just destruct the signals. If both are in the same pattern, then it construct the signal. So similar light in form of light waves, it is just included here. Quantum wave functions here mentioned in the figure. So in first you can see one, two, three. All three are in the constructive way. So it makes it as a linear combination of the three different signals and provides us on the next solution or the just to decision making, you can say. So interference basically keeps us to the particular point of decision making. Next is a quantum decoherence. It is a important principle, refers to the loss of quantum coherence when qubits interact with their environment, collapsing their superposition steps. If superposition not available but qubits working, then decoherence just comes into the existence. You can say it is a principle shown on the figure, decoherence principle shown in the figure, where you can see two cats are just um, actually attached, and you can decoherence both, then you can find out the both. On the other hand, if both are in the single set, then you can't find out both. So it is a simple actually uh, figuring to show the principle. Next one is a quantum tunneling. Quantum tunneling is just a principle where one or two or more quantum bits may go from one end to another end, but you can say that it is not breaking their class. It is not breaking their class. It is not going to outside the path. So when it is not going to the outside the path, it just maintain a tunnel. Such kind of principle considered as a quantum tunneling. And this effect considered as a tunnel effect. Okay, classical path and the quantum tunneling. It is just related with the each other. Okay, you can say when we imagine a ball on one side of a hill that can appear on the other side without climbing over it, define classical machines. So both principle of classic computer and tunneling is little bit related with the each other. Okay, sir, it is properly visible now.
Yes, sir. Yes, sir.
Okay. Next is a no cloning theorem. I have just mentioned at the time of saying the basic three principles. It is a principle of entanglement that provides us the opportunity for no cloning. Basically, that's why this theorem considered as a no cloning theorem. It is impossible to create an exact copy of unknown quantum state. This is due to the fundamental properties of quantum mechanics, which prevents the cloning of arbitrary quantum information. For example, if we have qubit in an unknown superposition state, we can't duplicate it perfectly. So ultimately, you can say, because actually both two bits both are entangled with each other, just making the a relationship between each other, you can't break or can't provide them another position. For example, we are just writing 1 and 0, so 1 and 0 both having the weightage here. If it is inclined little bit in one direction, that is it have a different meaning when it is inclined on the another direction. Okay, I think it is understood by people now.
Yes, sir. Yes.
Okay, next. It is now we are coming on to the implementation, because our software engineering challenge is just related to the implementation. That's why I'm a little bit saying about the implementation. It is only a single little program, you can say. It is a program on the Qiskit. Generally, I'm just providing Qiskit to my students working on the quantum club that is actually managed by me also. So Qiskit Python, using Python or the C, you can implement it. I'm generally suggest people to do in Python, and different gates. It is basically use of a Hadamard gate. It is a little bit program. You can see this program is just as per the language used by a general people. So QC here indicating the quantum circuit that is using qubit and the classical bit. One qubit and one classical bit. That's why it is mentioning as a quantum circuit 1 1. Using we are using here Adamard gate with the zero value. So QC dot H 0. It is measured by qubit 0 0. Here simulator just indicating the result and what will be the result. This is the little bit code, very little code actually. So it is just providing actually 1024 bits basically at the position of 0 and 1. If both are equal, then it is just splitting into the equal position. So 512 actually it provides in one direction. That's why output you are just seeing here as a 0, 512, 1, 512. Now question is that what was the problem about this implementation? Sir, it is a slide is changing properly now.
Yes, sir.
Okay, what is the problem in this implementation, on such kind of implementation, while algorithm is not very complex actually? So in the same code, I'm just explaining the same code. That code utilizing the superposition principle actually, not the all principle. Here I'm just utilizing superposition and the qubit only. So Adamant gate applies superposition, making the qubit exist in 0 and 1 states. You have seen already into the code 0 and 1 on the position of superposition. So I'll be using the Edmond gate. When measured, the qubit collapses to either 0 or the 1 probability. Here, a repeated run you have just considered How much is the maximum? 1024 shots. So that's why it is splitting between the 0 and 1. That's why output you have just seen 0 at with the 512 and 1 is 512. Next, now we are coming on to the applications that provides the challenges. Actually, I'm not coming on to the challenges right now. It is the basic application. In the cryptography, we just utilized Shor's algorithm, quantum key distribution. Shor's algorithm works just as a RSA algorithm, and entanglement just provides us key distribution because it is not generated again just like a hash function, you can say. That's why ID quantum employs quantum key distribution for secure banking transactions, you can say. Right now it is utilized uh, share market, basically uh, to predict the values and to make the portfolio of the people. Next one is the optimization problem, where you are just utilizing quantum approximation algorithms to solve complex logistics and scheduling problems. Okay, it is just utilized on the traffic flow actually managed by the Volkswagen using the quantum simulators. Next one is a machine learning. It is a most uh, interesting concept right now, application that is utilized by computer engineers. So quantum neural network basically improves AI models for pattern recognition and data classification. That's why quantum SVM just utilized to provide the accuracy. Here Google also working on it. That's why we have taken the example on the Google. Google AI employs quantum ML for image recognition. That is the one very popular actually concept given by the Google AI. That is the um, pi something. I'm just not remember right now the name, but you can very easily find out that. Next, drug discovery actually a very good application. That is a typical application for the supercomputers. When a little bit drug we find out, or the model we have to find out, then generally our computer, that is a GPU, uh, runs on the more than 1 month to find out a single solution. So it is a very good application of quantum computers to provide us a perfect module of the drug. IBM Quantum uses simulation for the some pharmaceutical industries also in the same way. Next is a financial modeling, that is the portfolio optimization. So Goldman Sachs, you can see that is the quantum, utilizing quantum algorithm for the financial modeling. Ultimately, you can say for the portfolio management or the portfolio optimization for any people. It is just considered into the uh, market fluctuations to minimize the risk in the market. That is a high, I think, into the um, India also, because a lot of things uh, affect the market in India actually. Next, logistic and supply chain management. It is the basically business that depends on the route or the optimized route. A business can run very smoothly if it having the perfect route, or maybe in difficulty when it is not having the correct route. So evaluating the multiple paths simultaneously using the route optimization algorithms. DHL just uses the quantum algorithm for supply chain efficiency. That's why I have just considered it. Next, now we are coming on to the our basic topic. That is not a very big, but I am just considered it uh, to provide some path to all the newcomers into the this particular field. challenges currently faced by the developers. So quantum computing is rapidly evolving, you can say, providing the engineering challenges that must be seen just when we are going to adopt the quantum computers ultimately. These are the challenges. Just I have divided into the two parts. First one is the challenges of category 1, second one is the challenges of category 2. So on principle and the environment, all the challenges considered in the challenges of category 1, while on the software development and the software maintenance considered as the challenges in category 2. Now challenges considered in category 1 to category 8, to the first to 8 actually I have considered as the challenges in category 1, while other considered as a category 2. Qubit stability and decoherence, it is just considered as a first challenge because qubit actually the building block of quantum computers are extremely sensitive to the noise. A little bit noise can just change the position of qubits that can actually uh, affect your output. This vulnerability leads to the decoherence, where the qubit loses its quantum state, rendering it useless for the calculations. That's why calculation actually can change. Engineers are working on this sophisticated techniques to shield qubit from the noise. Okay, so it is the major challenge because it is just uh, actually uh, takes us into the other challenges also. For example, error corrections, okay, or the fabrication. That's why it is a first challenge considered. Second one is a challenges of category 1 is 2, that's you can say scalable quantum systems. That is the increased qubit count, how you can increase the qubit. Okay, generally Qiskit when provides to the newcomers, Qiskit is a toolkit of IBM that is provided to the newcomers or the people interested in quantum computing like me or the new people. So all those peoples actually can utilize the 3 qubit, 2 qubit that is provided by IBM generally. Okay, so 2 qubit to 3 qubit to 4 qubit to n number of qubit, how we can go? That is the very big challenge actually, how we can increase the qubit count. The number of qubit in quantum computer must be significantly increased as per the requirement of the real world problems. So it is a first part of this. Second, connectivity and control, how to develop the method to connect and control the qubit or the large number of qubit. When we are working with the 2 or 3 qubit, then not a very big problem, but when we are going to utilize n number of qubit, 24 qubit, 132 qubit, that is very typical to maintain the connection and the control between these qubits. That is the actually uh, connectivity problems that affect the scalability of quantum systems. Next one is a system architecture. So designing efficient and scalable architecture for quantum computer is essential. You can say that is the increasing in the qubit count, how we can increase the qubit count and how we can manage it into the quantum computer or the quantum computer's architecture is a basically problem of scalability. Okay, next one is implementation hurdles. Next one is implementation hurdles. First one is uh, at the level of material science. Second one is at the level of fabrication. Third one is at the level of integration and the packaging. You can say a quantum computer, you can see just as a round shape or as a cubic shape, just you have seen in all the figures, I think so. So ultimately, which material actually you can utilize to maximize the qubits is a challenge. Second one is how we can fabricate these bits, okay, into the form of into the form of a chip with the minimal effect, you can say, and how we can integrate all the things and package with each other to solve the complex problems. Okay, next is a cost reduction and the accessibility. Reducing the cost of quantum computers is a crucial, basically because uh, qubit generation or the qubit increment is a very uh, cost actually affecting thing. Here how you are just making a 2 qubit computer having the very little cost, while the 3 just increasing exponentially. So n number of quantum qubit, actually if you are utilizing, then a high cost actually you are going to pay. That's why people, when using the mm, algorithm, just to utilize the simulator that is given by freely by the IBM. So I have just suggested people to use Qiskit also. Next, user-friendly platform. Actually, platform is not user-friendly. That is also a problem. That's why people are unable to access the full facility of the quantum computers or the full principles of the quantum computers. So, developing a user-friendly platform is also a task. Okay. Next, it is very important, that is addressing the workforce shortage. People actually working on the computers or the computing, not working on to the quantum computers, because uh, people just generally works with the help of mathematics, but not with the help of physics. While the quantum computers basically depends on the principle of physics, okay, on the basically depends on the principle of physics. On the other hand, simple cryptography or simple applications of computer or the classic computer just depends on the principle of mathematics. Those are using the probability, those are using the random number generator, but here you are using the principle of superposition, you are using the principle of entanglement. That's why actually workforce not generated properly, because people not going into the coding field from the physics background. It is coming to the coding field from the mathematical background generally. That's why in education and training, expanding education and training programs to develop a skilled workforce for the quantum computing industries basically. Next, research collaboration. People in the teaching is not actually involved with the industry. Actually, industry or the academia collaboration is not available uh, in India at least. So that's why you are not able to generate the proper workforce in the same field. Next one is a quantum computing and AI. You can say AI right now using a lot of techniques to generate models. But in case of quantum computers, you are unable to integrate a lot of algorithms, excluding the Shor's algorithm or few well known algorithms. You are unable, I'm also unable to interact the RTAI with the quantum computers. Okay, that's why quantum computers can accelerate the training of AI models, but we are unable to integrate both mm, into the just generate a particular correct decision. Okay, that it is a basically problem. So seamlessly bridge a quantum computing is a research area or the key research area to develop new concepts actually. Next one is a achieving quantum supremacy and the demonstrated use cases. Actually, supremacy right now available, you can say, for the algorithms at the Google, and you have to, or the we have to break that supremacy. Then we can go ahead from the Google. That is right now not possible due to the limited resources basically. So demonstrated use cases not available properly, developing practical and impactful use cases that showcase the real world benefit of quantum computing is crucial basically. Next, quantum supremacy, that is also a big challenge for us, that provides a big milestone actually. Next is the error correction and the fault tolerance. It is also I have discussed in initial slides. Quantum computers are inherently prone to errors due to the fragility of qubits due to what? Due to the noise actually. Developing robust error correction methods is crucial here. It provides faults, so fault tolerance is essential for building a large scale quantum computers ultimately. uh, that's why research efforts also having a focus to develop the error correction techniques also. Okay, next, now we are coming on the challenge that is related to the software engineers directly actually. So, what is the quantum software engineering? It is just, you can define as the use of sound engineering principles for the development, operation, and maintenance of quantum software. Okay, it is the challenges you can see uh, SQE perspective. When it is related to environment, it is related to community, it is related to degree of realism, it is related to comprehension, it is related to theoretical ground, it is related to code quality, it is related to implementation of code quality. That's why this full figure actually managed for the challenges. These are the basic challenges actually. Now we can go quantum environment. Challenge number two, it is a quantum environment, hardware and the software. Quantum environment encompassing both hardware and the software. Right now you can divide into the three portions. First one is a framework, second one is a integration, and third one is a execution basically. So it is just divided into the three parts. First one is a framework, second one is a integration, and third one is a execution. Here framework actually a very big challenge to provide the API design for the quantum technologies. For example, when we are using the tool Qiskit, and we have not actually standard to make a framework for the particular tool actually. Next one is a integration of quantum systems with the traditional is not that easy actually, because we have to shift from the classical computer to quantum computer, not to the jump from directly to the quantum computers. So we have to just correlate our classical computer to the uh, quantum computer. That is also a very big challenge when we are just going to work for the quantum computers to make a blockchain network or other actually. That's why setting up a execution environment and the simulation is basically a challenge. Next, what a developer seen in this overall process, it is just having the difficulty in debugging the algorithms, because in the traditional debugging method, troubleshooting performed for a particular state. However, here state is not able, we are not able to avail the particular state actually. That's why it is a big challenge to just debug our algorithm. Quantum mechanics concept like superposition or the entanglement prevent the direct observation of program state. That's why troubleshooting is a very tough task in case of quantum computers. Okay, next one is a unique programming paradigm. Quantum programming language differ significantly from the other languages like C or the C++. This deals mainly with the logic, and logic just based onto the mathematics, while here logic's coming from the physics. That's why quantum languages are too much different from the other classical languages, because it is using the qubits. In the classical computers, you are using 0 or 1 to design a logic, while here you are using the qubits, that is a number of qubit, n number of qubits, or the quantum gates. Okay, this necessity a fundamental shift in approach for developers basically. Next one is a resource constraint. Quantum software development is significantly more resource intensive than the classical development. Okay, next. Next one is a quantum coding challenges. It is also again divided into the two parts. First one is a implementation and second one is a code quality. These issues are related to the integrated development environment and compilation. First one is a how IDE or the integrated development environment can be implemented. It will be a game changer when we are able to make it perfectly uh, friendly for the developer actually. Second one is a it's a compilation of a program using that particular IDE for the complex processes. It is also a challenging task for a developer. Second thing is a code quality issue include problem related to the debugging, testing, readability, and the maintenance also. That's why maintenance of code. Okay. So debugging, testability, and the readability ultimately a task that is a challenge, because qubit works with the registers and the gates that is different from the register and gates available by used by by a classical computer basically. That's why it is creating a code that is may or may not readable to the general people actually. That's why it is a very big challenge actually, because code readability is a main issue to learn something actually. Next one is, that's why we are just trying to bridging that gap, and it is basically Talavera manifesto actually utilized to that bridge that purpose actually. Manifesto just says that principles and roadmap about um, the quantum software engineering just to develop for the newcomers. Next one is iterative software development, how to design a software that can increase itself or just quality, provide the quality to itself is a challenging task ultimately. That's why formalism also available. By combining these two approaches, these are basically different approach. First approach is a iterative modeling, just like a iterative model used in software engineering. People also from the computer background just know the SDLC different, and the waterfall model or the other approaches, iterative modeling. So same kind of modeling, iterative software development. And second one is a formalism. These are rigorous method, just development of a theorem, proving and model checking that mathematically ensure the correctness of the software program. So to these two basic approaches you can utilize to develop your quantum software basically. Next, now we are going to finish it. And these are the future advancement of quantum computing, you can say Google's quantum supremacy. In 19, Google's processor achieved quantum supremacy by solving a problem in 200 seconds that would take 10,000 years on a classical computer. Okay, so you can say it is a very, very big milestone given by Google. 10,000 years time just reduced into the 200 second. So it is a challenging task to other developers. Next one is a recommendation system. A hybrid AI quantum models that is developed to provide the recommendations. Because in the future system that could scale a massive data set actually. So just to examine that data set, we have to make some recommendations. Okay, that is also a task. Now it is just going to finish. So ultimately, quantum computing represents revolutionary advancement, you can say, revolutionary principle for the real world applications, you can say, demonstration and implementation you can utilize with the Qiskit for the initial days and the uh, next stage. Actually, I'm also waiting to see something. Thank you very much. If you have some questions, then please let me know.
Participants ask, if you have any question, ask them. Thank you, Dr. Neeraj Kumar sir,
Okay, thank you, sir.
for this insightful and thought-provoking session for discussion on the engineering challenges in quantum computing development has truly shed light on the hurdles and innovations driving this field forward. To our participants, we sincerely appreciate
Thank
your attention and engagement throughout this session. Once again, thank you, Dr.
you.
Neeraj Kumar sir, for your valuable time and knowledge. Thank you also
Thank
to
you, sir.
all our participants for your continued enthusiasm. Thank you.
Thank you very much, sir.